pair using transformer and RNN LSTM models, which will be followed by Amharic caption generation from Holy Picture
Ethiopia, and there is a need for the effective machine translation between them. When Afan Oromo is served as working language of Oromia regional state government, while Amharic is as official language in the federal government and in Amara regional state. So in order to address the translation between these languages, it is better to develop the machine translation between these two languages. Different approach have been explored in the machine translations, which include the corpus-based mass translation, rule-based machine translations. When we say the rule-based translation, it relies on the language expert to develop translation rules, while corpus-based machine translation tries parallel corpora prepared by the language experts expert to automatically extract the knowledge from the given data. Another one is hybrid machine translation approach. It also have been developed by combining the strengths of both corpus-based and the rule-based machine translations in order to increase the translation quality and the fluency. Currently, deep learning is a data-hungry method. To be more precise, current neural machine translation algorithms are only drawn to pattern that are like what we have already observed. The quality of the output from this deep learning or deep learning based translation of the model is dependent on the quality of the input data based on the input data. While we get the quality of the data, we get the quality of the outputs. This machine translation or these models have the encoding which is required for any neural machine translation that passes a raw text in either .txt format or CSV format. So since the computer can only process numerical data with, and it process this text, the raw data have to be converted into the format that computer can understand. The motivation of this work is by the present neural machine translation models needs more data. We create a new Afan Oromo-Amharic machine translation dataset and utilized it to train our models. We must ensure that every line pair in the parallel language pair matches the translation phrase in the parallel dataset during the preparation of the dataset. To achieve this goal, the researcher tried to create a new dataset in the Lao research language, that means Afan Oromo and Amharic, again to ensure the proper data input and improve the translation accuracy between the language specialist provide the prepared dataset. Then to train our models, around 20K of Afan Oromo and Amharic parallel sentence will be used in these papers. Therefore, the objective of this research is to design and develop deep learning-based Afan Oromo-Amharic machine translation. This will be achieved by the preparing parallel corpus, identifying best model for translation, adopting the existing neural machine translation models. Then developing neural machine translation models and evaluating the developed models performance. By addressing the limitation of previous study, by employing the advanced deep learning technique, this research aims the translation accuracy and the fluency between Afan Oromo and the Amharic language. Another one is the contribution of these works. The contribution of this work mostly pertains the earlier research examined in those authors, but the primary difference between our work and other work is that we employ the newly created dataset for our owns. This guarantees the best possible quality for the input dataset and offer the improved translation quality. An additional distinctive aspect of this study is to continue optimizing the particular when utilizing the Bose model, that means transformer in the RNN model. Again, specifically, we have created the first ever 20K Afan Oromo-Amharic dataset that support the researcher in the field of machine translation. This is a unique contribution of this work. Again, the developed transformer and LSTM model for Afan Oromo and Amharic machine translation, which support the media outlet broadcasting in their language. We have demonstrated the effectiveness of our developing model for Afan Oromo-Amharic machine translation that lead notable important translation quality compared to the earlier study that used their dataset. Another one is related work. Classic encoder and decoder based RNN recurrent have the problem with exploding the vanishing gradient. To solve this issue, this author associate the present novel method for using self-normalized neural networks in the transformer. The research has demonstrated notable advancement in neural machine translation using attention-based that simultaneously align and translate the given text. In addition to translating data, attention-based neural machine translation attain the context information from the decoder encoder and the concatenate it to the next output. In order to simultaneously model the source target context translation, again this author proposed a topic attention using the phrase context representation. Another authors or these authors investigate the use of the very deep transformer model for neural machine translation. They introduce the technique called admin for initializing deep transformer in the conduct experiment on English, French, and English German translation task. The result showed that very deep transformer with up to 16 encoder layer and 12 decoder layer can be effectively with significant blue score improvement compared to the shallower models or the previous models. However, the study did not specifically focus on the Afan Oromo in the Amharic language. However, there are a lot of researchers conducted the machine translation on Ethiopian language. From that, Akubagzi focused on the Amharic to Tigrinya machine translation using hybrid technique. They conducted the experiment with statistical and hybrid approach with hybrid approach outperforming the statistical approach in the term of blue score. However, these authors study focused on syntax reordering and the lack morphological rules. While Galana Turlu conducted research on the bidirectional Amharic to Afan Oromo machine translation using hybrid approach, their statistical approach achieved high blue score for translation language. However, this study also did not include the complex sentence in evaluations. Another author, Imabet Girma, investigated the effect of morpheme and the word level alignment on bidirectional Afan Oromo-Amharic machine translation using statistical machine translation. The study highlighted superiority of the morpheme level alignment in terms of blue score compared to word level alignment. However, the study faced challenges such as use of the word alignment for training the system and the scarcity of the diverse for the study. Some studies have shown promising result in machine translation between Afan Oromo and Amharic. However, there is a gap in addressing the translation of the complex sentence. They are prevalent in the real-world scenario. Though the future research should aim to incorporate the complex sentence structures into the machine translation model to improve their applicability. The morphological complexity of an Oromo and Amharic language presents significant challenge in the translation, while some studies have explored morpheme-based segmentation. There is a need for the further research optimize a rule-based morphological segmentation or machine learning algorithm to enhance the translation accuracy. Material and the methods. Design science research is selected as a general approach to design and develop bidirectional Afan Oromo Amharic machine translation. This design science approach contrasts to behavioral result paradigm, which concern with describing, explaining, and predicting the individual organization or social effect of technology. Design science is concerned with the systematic creation of the knowledge and the design as intentional, intellectual, and the creative problem-solving activity. This design science contain design prototype to ensure the development system was implemented as well as to enhance. So well-known approach that work for design science research is experimental researches. According to this research, in our work, for experiment will performed by two models. That means LSTM and the transformer, which is selected in these workers. Both models have encoder and decoder to model the language, and they can learn syntactically related word for the sentence. Attention mechanism incorporated to LSTM by these authors that was proposed as a solution to limitation of the encoder decoder model, encoding the input sentence to one fixed length vector from which to decode each output in time step. Another one in the transformer positional encoding theirs, which is applied for enhancing the modeling ability of sequencing of the words. Again, this made the compensation for the inject word order information into the feature vector, which can be avoided to become the variant sequence ordering in transformer. That is why we select this transformer in the LSTM. In the following diagram, it shows the structure of LSTM transformers, which is composed of fundamental parts, that means encoder and decoders. The encoder work accepts the sentence or source sentences as a word embedding and convert it to the representation, while the decoder generates the output probability from the word based on this representation and the word embedding of the previous generated tokens from the output. This is the structure of the transformer models, and this is the LSTM models. After the model was trained with the cleaned dataset, we plotted learning curves that is shown in the figure 2 up to 3, that's showing the learning curve of both LSTM and the transformers with accuracy in the loose graphs. The graph shows that for each of the two models, transformer and LSTM on the language pair, Afan Oromo and Amharic, we plot the label with A represent the loose curves, with the B is reflect the accuracy curves. Again, additional information, the orange graph depicts the validation curve, while the blue graph displays the is the blue score, the graph accuracy in the loose graph of both transformers and the LSTM. These experimental result and discussions. As we say in the first time, we used two models to perform the experiments, LSTM and transformer for both bidirectional Afan Oromo and Amharic machine translation to get better performance of the translation. From the result, it showed that LST model-based translation, while Afan Oromo as a source language, we get around 8.72 blue scores, while the reverse or the vice versa, when Amharic used as a source language, we get around 10.3 percent of the blue scores. While the transformer model used for the translation around 1.8 around 18.5% of the blue score is recorded when Afan Oromo is used as a source language, and the 21.2 blue score is recorded while Amharic are used as language. So from this, we understand that transformer performs based result, while when we compare the direction of the translations, when the Amharic are used as source language, transformer can perform better results than LSTM. This prototype developed for the transformer models. This is the output samples, calculated text from both models. Okay, conclusion of this work is our research aim to design and develop bidirectional machine translation system between Afan Oromo and the Amharic language using deep learning techniques. We adopted neural machine translation approaches, which employed an end-to-end deep learning framework. To accomplish this, we collected and pre-processed the parallel corpus consisting of 20 case sentences from various online and offline sources. For the task of bidirectional Afan Amharic machine translation, transformer and LSTM are selected. Transformer are selected as a model of these works. Four experiments were conducted using the optimized parameter, and the quality of translation sentence was evaluated using the blue score. The results showed that transformer model achieved the blue score of 18.5 when translating from Afan Oromo to Amharic, and the 21.2 when translating from Amharic to Afan Oromo. In contrast, when we use LSTM model, blue score attained of 8.72 for Afan Oromo to Amharic translation, and the 10.39 for Amharic to Afan Oromo translation. Based on this finding, we conclude that transformer model outperform LSTM model in terms of blue score for the limited language data limited language like Afan Oromo and the Amharic languages. Again, when we see the translation, the result will be scored in the while Amharic are used as a source language translation. Another one is recommendation. The recommendation of this work is to increase the corpus size. We have to increase the corpus size to get the better results in terms of accuracy. Again, we have to integrate the spelling and the grammar checkers for those languages to overcome or to get better data set or better text from the both languages. Again, another one is we have to utilize the domain specific data. We have to use the domain specific data. Since the deep learning can be based on the domain specific data. Thank you this all for attention.
Thank you, Arba, for the presentation. So he has joined us via Zoom, so he is online, so we can have questions and answers. I would like to start by requesting information regarding the data collection methodology that you followed. You stated that the already existing data set is not proper and it's not usable. So you said you collected 20,000 parallel sentences. So how did you make sure the translation is correct and the data is usable not only in your research but for other researchers as well?
Okay, thank you for the nice questions. After we collected that data, we have given to the experts to take to translate that data, and they check the correctness of that data. The experts, we used around 5 experts to check the collected data whether it's correctly translated or not.
I mean, have you made this data available for other researchers? Because it would be helpful for other researchers to get such a data and undertake other research as well.
Yeah, it's available.
Okay. Considering the morphology of the Amharic language in your presentation as well as in your documentation, I did not see any methodology that you have employed to handle this morphological analysis. So how did you tackle this issue?
Okay, I will take that. I haven't included on the document, but I handled the morphology of Amharic by normalizing using the available already developed morphology for some normalizations, because Amharic have many data, which have different morphology. So I have normalized. I will include on the document that I will take as a comment.
Questions from the audience?
What is it going to take to move it up to 1? Regards to the accuracy. So you went up significantly, right? From I think it's 8%. Now you're about 20%. So how do you what do you need to move this thing up to close to 1?
Sorry, again, I haven't seen from the technique.
The accuracy of the model.
Okay. Yeah, the accuracy of the model is somehow it is minimal. But to increase the accuracy of the models, we have to increase the data set. When we increase the data set, again, by optimizing the parameters on the models, we can increase the accuracy of our model. Since the deep learning algorithms, they are, as we said in the first time, they are data hungry. So our data set is minimum when we compare to the other languages. That is why the result becomes the same.
Thank you, Arpa. Any other questions? If not, we would like to thank Arpa for the presentation, and we'll go to the next presenter. So the next presenter is Agenyo Teshome. Agenyo. The other presenter is large language model for mental health disorder by Wasihun Admas. Wasihun, or his colleagues Yirga, Aleka, Mabtu, or Fevel. Then the fourth presenter is speaker identification in Amharic language using spectrogram images, exploring deep learning techniques by Berhane Selassie. So thank you, Berhane Selassie. So as usual, you have 20 minutes to present your work, which will be followed by 10 minutes of questions and answers.
Okay, thank you, Mr. Chairman. Good morning, everybody. My name is Berhane Selassie Abebe, and currently I'm a PhD student in language technologies at Addis Ababa University. And today I'm going to present to you one of our works entitled Speaker Identification in Amharic Languages using spectrogram images, exploring deep learning techniques. Sorry. This is the outline of my presentation. Okay. Speaker identification is a process of identifying individuals from the unique nature of their vocal characteristics, and it has wide applications in the areas of security, forensics, and voice assistants and others. A large number of studies have been conducted on speaker identification using traditional techniques like hand-crafted features and statistical methods. However, substantial improvement have been observed due to the rapid development of deep learning in the last few years. The majority of these previous studies have focused on high-resourced languages like English and Turkish. But for the Amharic language, which is the official working language of the federal government of Ethiopia, there is less attention on using speaker identification, on using deep learning for the speaker identification task. So the objective of this study is to explore deep learning techniques for Amharic speaker identification to leverage spectrogram images in order to obtain both the temporal and the vocal characteristics of speech, and to assess different deep learning techniques, which are custom designed model and some pre-trained models. In our study, we have used a publicly available data set, which is the Amharic emotion detection data set. Although this data set was originally created for emotion detection purpose, it can also be used for speaker identification because it has recordings from varying number of speakers. So we have audio recordings from 65 speakers, and sorry, the in order to generate the spectrogram images, we have used a short time Fourier transform to convert the audio signals from time domain to frequency domain. And each audio file was converted into a 128 by 128 pixel image, spectrogram image. The models adhered a uniform hyperparameter settings and training configurations. And we then split the data set into training, validation, and test sets in the ratio of 80-10-10. As I said, we have trained and tested 4 models. These are custom CNN model and 3 selected pre-trained models. In our case, we have applied augmentation on the spectrogram image, which was recommended by one of the previous studies due to the simplicity and the speed. All the models were evaluated based on the accuracy metrics. We have also computed confusion matrix of the models in order to get better understanding on of the correctly and misclassified classes. This is the architecture of the custom CNN model. The input layer accepts a spectrogram image of 128 by 128, which has 3 channels. We have preserved the color because we thought it has importance in capturing some information, especially regarding the emotion, and we haven't changed it to grayscale. The input layer is followed by 3 convolutional layers, which have 16, 32, and 116, 32 and 128, 32, 64, and 128 filters with 3 by 3 pixels, which are used in order to progressively learn the more complex and abstract local features from the input image. And each of these convolutional layers, which are represented by the green, are followed by max pooling layer, which is represented by the red color, that uses sliding 2 by 2 window over the image in order to minimize the spatial dimension to help the model in order to concentrate on the most important features. The flatter layer converts the output of the last max pooling layer, a one directional vector of size 25,088. And following that flatter layer, we have a dense layer with 2 256 units that is used in order to learn high-level features from the input based on the previously obtained features from the preceding layers. Next to that, we have okay. In order to avoid missing some important information, I mean, we haven't placed it next to any of the preceding layers, but only after before the final prediction. And lastly, we have the output layer, which has 65 units belonging to the 65 speakers, and it uses the softmax activation function in order to output probabilities to each of these speakers. We have conducted dual set of experiments, one based on the original data set and the other one based on the augmented data set. And as I said before, the models have adhered uniform hyperparameter settings, and we have trained the models specifically by applying epochs in increments of 10, from 10 to 100, the Adam optimizer, learning rates varying from 0.001 to 0.0005 and 0.0001, and batch sizes of 16, 32, and 64. And optimal results were consistently observed across all the models when trained for 40 epochs and learning rate of 0.0005 and batch size of 32. This is the result of the models when trained on the original data set and the augmented data set. As you can see from the table, the ResNet, the pre-trained models performed better than the custom CNN model in the non-augmented version. All of the pre-trained models performed better than the custom CNN. However, when we look at the custom CNN, whenever the custom CNN has improved performance on the augmentation, all of the pre-trained models declined. We concluded that the augmentation has helped the custom CNN in order to achieve better learning and generalization. And the augmentation just did only introduction of noise and made a conflict with the already learned features in case of the pre-trained models, and this could be probably for the complexity of the pre-trained models, and it might require other additional augmentation techniques. When we look at the losses, the ResNet 15 and DenseNet 121 obtained the least losses of 0.31 and 0.41 respectively, indicating their better performance. And when you see the custom CNN, it achieved decreasing the loss from 1.02 to 0.92. And if you look at the training and validation accuracy and loss curves, as you can see on the left bottom, Generally, the validation accuracy of the augmented CNN has got a higher validation accuracy over epochs, indicating that the augmentation has helped it in order to better learn and generalize. And the same story can be observed from the loss curve as well. In the right bottom, you can see augmentation enabled the model in order to consistently decline both the training and validation losses. And that means that augmentation has made the model in order to get applied on diverse data set. This one is the validation, training and validation accuracy and loss curve for the best performing model. The best performing model is the ResNet model. It has achieved an accuracy of 94.74% on the non-augmented data set. As I said before, the augmentation declined the performance of all of the pre-trained models. As you can see from this curve, initially it has shown some fluctuation, indicating some instability, but ultimately it has reached the highest accuracy and the least loss. And this is the confusion matrix of the augmented CNN. And we can see that this confusion matrix shows dense entry along the diagonal, indicating that most of the classes are correctly classified with some sparse misclassifications. And you can just compare it with the confusion matrix of the ResNet 50 model, where we have even fewer misclassifications with more dense diagonal on the chart, indicating that that model has performed well and classified most of the classes correctly. Generally, in this study, we have demonstrated the application or the deep learning can be applied for speaker identification in Amharic. And we have obtained that the ResNet 50 pre-trained model achieved the highest accuracy. And one important thing that we have observed is the augmentation has helped the custom CNN in order to manage overfitting by minimizing the loss. Some of the recommended feature works include expanding the dataset size and diversity for better model training, exploring custom architecture specifically designed for speaker identification, comparing and fine-tuning different deep learning approaches for better results, and explore different data augmentation techniques, because the techniques that we have applied might be not the appropriate one. And these are some of the things that we have recommended. Thank you. These are the references that we have used for our study. And thank you for your attention.
Okay, thank you, Brian Selassie, for the wonderful presentation as well as the efficient usage of time. So now it's time for questions and answers and discussions. So.
Thank you very much, the presenter as well as the Mr. Chairperson. I do have a few questions for you. The first is, how many speakers are there in your corpus? The second is, I think the customized CNN, you fine-tune epoch, learning rate, and the like hyperparameters, but how do you set the number of convolutional layer, the number of max pooling layer, the number of dense layer? How do you set it? I think you use 3 convolutional layer. How do you get that 3 convolutional layer? Because number of hidden layer is 1 one of the hyperparameters that need to optimize in deep learning models. So how do you set these hidden layers, convolutional layer, marks layer, as well as the dense layer? Another is, I think, use the pre-trained. Are you use the pre-trained model as it is, or are you customized to your data? For example, DenseNet has around 121 layers. Are you use exactly this match layer for your data, or are you just doing something for your data? And another question that you applied data augmentation to increase the number of corpus. Yeah, what data augmentation technique really utilized for your data augmentation? The techniques that used. Finally, I think you reported that RSNet 15 is better than the other models. Up to me, I expect that your customized CNN model is better than the pre-trained model in terms of performance, because your data is small. You develop your own CNN which is fit for your data. So the performance of the customized CNN model is better than the other pre-trained model, up to me. But you report that RSNet 15 is better than all the other pre-trained model as well as your customized model. What is the reason behind it? These are the questions. Thank you very much.
Okay, maybe I'm not going to keep the order, and you will remind me some of the pointers because there are too many questions. The first question is, I have already indicated there are 65 speakers. From these 65 speakers, we do have around 2,474 recorded speeches. Regarding the second one.
Hyperparameters.
Hyperparameters,
the number of
yeah.
hidden layers.
Yeah, regarding the number of hidden layers, maybe we wanted to make it simpler. And this is, I think this is the first task in applying deep learning, specifically on emotion data set. As you know, emotion data set is going to introduce complexity to the speaker identification task, because when you are working on a neutral speech, that is simpler. But whenever you are going to have different emotions, in our case, for example, in the data set that we have used, there are 5 emotions: sadness, happiness, anger, neutral, and fear. And whenever we have these emotions, even the speech spoken by a single individual will vary. The same speech will vary, and that will introduce complexity. And regarding the questions that you have asked regarding the complexity of the data set, you can also consider this one into consideration. You can take this one into consideration. Even if the number of recordings is 2,474, we have this thing in it. We have used 3 convolutional layers followed by 3 max pooling layers inside. And we have also added a dense layer with 256 units after the flattened layer. And maybe that can be improved. And
my question is, why not use 2 convolutional layers? Why not use 4 convolutional layers? Why not use 10 convolutional layers? So you need to fine-tune it, the number of hidden layers to your data. That is my question.
We have tried some numbers, but we have got better result when we work on 3 convolutional layers. We have made number of experiments, and we reached this point after getting some results from these experiments. Can you remind me the third one? Sorry, I'm having a little memory.
Data augmentation technique did you use?
Okay, the data augmentation technique, just like the layers, we have tried to apply different data augmentation techniques, but lastly, we have used only random vertical and horizontal shifting with pixel filling. When we apply other additional augmentation techniques like scaling and others, it impacts the result, and we just omitted that one.
I think the result that you attain at the end of the research is RSNet 15 is better than your customized as well as the other pre-trained models. What is the reason behind it, considering your data set size?
What we concluded is, on the original data set, actually the RSNet 15 worked better. But when we added augmentation on it, the performance declined, which means that the introduced noise just conflicted with already learned features, and it impacted the performance. So it is not the result of the RSNet model that has a problem. Maybe it is the augmentation that made it to have that declined result. And in general, we have got better result from that model when it is working on the original data set. Regarding whether you have customized, you have manipulated it, we haven't manipulated it, but we have added a dense layer and average pooling layer uniformly to each of these pre-trained models. We didn't do anything else. Can you remind me the other? Sorry.
So we have other question from another participant, so please.
Okay, thanks a lot. I have two questions. So one is regarding the data augmentation. You have said that you performed the data augmentation on the spectrogram image, not on the audio signal, right? So how can we say an augmented spectrogram image is representative for the speech of a person? And how can we say a model learn features for speaker identification task while you are performing the data augmentation on the spectrogram image? Second question is regarding to the model. Aren't there state-of-the-art models that can perform better than the CNN family for speaker identification task? For example, transformer families like vision transformers and swing transformers that can perform better than the that you have adopted for your research. Thanks a lot. Only two questions.
Okay, thank you. Yeah, as you said, we could have done the augmentation on the audio file. That is one important point, thank you. But we didn't do that one because, as I have tried to indicate earlier, performing the augmentation directly on the spectrogram image is better as it is recommended by one previous study. That was what we have followed. There was an existing study that recommends performing this augmentation on the spectrogram image directly. But actually, as you said, that has, even though it helped the custom CNN, it just declined the performance of the pre-trained models. And as you can say, as you said, this can be taken as something that we can do in the future in order to just get a different result. Regarding the second question, why don't you try other models like transformer, which are performing better than? Yeah, we didn't want that one because we wanted to just focus on the CNN model and see how we can achieve a result that can be compared against the pre-trained models. We haven't done experiments using the transformer.
Okay, thank you. Any other questions?
Okay, thank you. I have two questions. The first one is, I think you have trained your model from an image generated by spectrogram. So where the speakers speak different words, for example, it will give you different pictures, right? So how can you say that for different words it will work for the same person? Because your model, you trained your model on some words maybe, so it might because from my understanding, visual CNNs will try to capture some the features from the image. So wouldn't it better to use just a normal classical methods like directly from the signal to detect the speaker? That's my first question. The second question is, you are developing a speaker identification model. So for speaker identification model, then if we want to add another speaker, are you going to retrain your whole model? So how are we going to apply this in real world? Thank you.
Okay. It is not only this study that is using spectrogram images. Spectrogram image is, by the way, a common method for speaker identification or speaker recognition in other related studies. And we did our study on this one because we have been working on image processing task, and we wanted to relate it together with that task. Regarding the other one, what was the other one?
If there is an additional person, do you need to retrain the system?
I don't know what you mean by that one, but always what we do when we train a model, we do have a data set, and we split our data set appropriately into different sections: training, validation, and test set, and we train on that one, and we get a model. Then we expect that the model is going to just give us an output to a given input. And I don't know why you are asking that question.
If I may, the reason I think he's asking this question is usually when you have to train throughout using all the data, all as new, it usually takes a lot of time. So there is a concept of retraining or using the model and only training based on the additional data that we get. So is your system developed in such a way, or if there is an additional person, then we have to retrain it from scratch again?
Yeah, actually, our model is based on an already existing data set that is publicly published. We have used that data set, as I said, and the way we train it is only in regard to that data set.
Any other questions? If I may ask a little bit about the data collection methodology that you have used. In speaker identification, one of the challenges that we face is noise, which you have briefly stated in your documentation. Have you considered different kinds of noise as well as the location of the microphone? Because such speaker identification applications are currently being used for minute-taking applications to identify who is saying what. And in such cases, the location of the speaker will be different and the type of speaker being used will be different. So have you considered that in your data set? I assume based on the total data that you stated, which is 2,474, it is a text-independent system that you have to try to develop. And my question is, if there is a speech of this 2,470 performing as well as you stated in your document. And another thing is when you apply your system, is it one speaker at a time and then you identify, okay, this is a speaker? Or is it multiple speakers in one conversation where you identify, okay, person A is talking, okay, then person B is talking? Is it a continuous approach? Thank you.
Okay, thank you. Regarding the noise, we have just used the already available speech data set. We haven't manipulated the data set. We just converted the existing data set into spectrogram image. Regarding the
microphone location,
yeah, as I say, this same answers that one, because it is not our group that created the data set. It is already public data set. Regarding the,
is it one person at a time or multiple person?
It is one person at a time. We want to just identify who is speaking that speech.
Okay, thank you, Birhane Selassie, for the presentation. Okay, so now we will have a 15-minute tea break, and then after that we'll meet here and we'll have one keynote speech, which would be followed by a ceremony. So now it is 10, so let's meet at 10:15. Thank you.
Check. Oh, yeah. Check. Mic check. 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 Mic check. 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 Mic check. Mic check. 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 Mic check. Oh, yeah. I think ድምፁ ስለሆነ መሰለኝ። የዚህኛውን ማን ነው? ጌኑን ትንሽ ጨምር። ጌኑን ጨምረው። ማይክ ቼክ ማይክ ቼክ ማይክ ቼክ 1 2 3 ማይክ ቼክ ማይክ ቼክ 1 2 3 1 2 3 1 ማይክ ቼክ 1 2 3 1 2 3 Mic check, mic check, mic check. ይሰማሃል እኔ ጋ? Clear ነው? አዎ። ሳወራ ይሰማል? Clearly አይደለ? ኦኬ በቃ የጌኑ እውነትን ነው? ዋው እሺ ቆይ ምንም ስታቲክ የተፈጠረ አይደለም ምንም ነገር ወይም ቆይ ካሜራ ካላቸው ወይ ሪኮርደር ካላቸው እስቲ እሺ ቼክ አድርጋ እሺ
ይሰማል? ሄሎ hello.
more languages, de-list using critical, cultural, and linguistic guidance. So in this talk, I want to mainly focus on our recent work called Massively Multilingual Speech. It is a joint work with so previously, before MMS, popularity of the 7,000 languages, we have any speech for speech technology. So with MMS project, we actually 10x the amount of languages that were supported by speech technologies. So here I present a map of all the coverage of all the languages that we introduced with the MMS. So you can see that we cover speech to text, text to speech, and language identification for many languages across the world. So the way it works is we leverage self-supervised training, which the main idea here is that without having to have like large amount of supervised data, we pre-train with some amount of unlabeled data, with a large amount, potentially large amount of unlabeled data, and fine-tune with maybe high quality, some few hours of high quality labeled data, and get pretty good results that we show that I show later in the talk. So at a high level, MMS provides data for about 1,100 languages, and in labeled as labeled data set, and also 4,000 languages as unlabeled data set. We also provide pre-trained wave-to-vec models covering 1,400 languages, and automatic speech recognition for about 1,100 languages, text-to-speech also for about 1,100 languages, and language identification for 4,000 languages. So now I'll talk about the data part, like how we're able to like train these models on such large amount of languages. So we rely on religious texts which are available in many different languages, and create two different data sets, MMS Lab and MMS Unlab. So MMS Lab is the labeled data set, and MMS Unlab is the unlabeled data set. So for the MMS labeled lab data set, we take recordings of New Testament in over 1,100 languages at an average of about 32 hours of data per language. So we had to do some processing on top of it to make it usable for the machine learning models. For example, we take these long audio recordings and segment them into like smaller recordings so that we can input them to the machine learning model. We also had to work on like many unseen languages where we didn't have any like force alignment systems available. So we use this tool called Uroman, which can convert the script from any language to English, basically like it translates to like Romanized characters, so that we can work in a common space for like all languages. So this helps us tackle all the tackle all the languages that were not seen by our models. Also, we develop a GPU-based force alignment algorithm so that we can do this force alignment at scale on about 50,000 hours of data that we have. So overall, like MMS lab dataset consists of about 1,100 languages, which consists of like 50,000 hours and about 10,000 samples on average per language. We also, as I mentioned, like we also have this unlabeled data set covering 4,000 languages. So for that, we take various religious recordings in 4,000 languages. So one main challenge using a religious data set is that most of the speakers which speak the text is male speakers. So we wanted to make sure that our models doesn't have like any bias towards like a particular gender. So we trained our models on this data set, which is dominated by like male speakers, but we test the performance on both male and female genders, and we see that the performance is not vastly different. You can see that for female we have like about 12.4% character error rate, and for male voices we have like 12.3. So there is no particular bias towards any gender. So now I'll talk about all the tasks that I mentioned, the speech recognition, text-to-speech, and LID systems that we built. So for the automatic speech recognition system, we used wave-to-wake 2 models. We trained 2 variants, 300 million model and 1 billion model, on about 1,400 languages. So for training these models, we use the MMS labeled, unlabeled datasets that I mentioned before. But we also combine it with many other open source datasets that are available. To improve the performance, we also like fine-tune this dataset on high-quality labeled data. And we also introduced some adapters so that we have introduced some language-specific adapters so that we can improve the performance even further. Also, like once we train the models, we decode them using n-gram language models so that we can boost the performance even further. So I'll compare this. We compare this system with Whisper, which is also like very popular open source speech recognition system. So if you take the common set of languages which are supported by Whisper and MMS, we can see that the MMS model has like makes less than half the error rate compared to Whisper. So on about like I think 54 languages that we tested. Also, one important thing I want to mention here is like Whisper is pretty good on like English, like all these high resource languages. But if you take a look over all the languages, right, like all the 54 languages, our model is much better than the Whisper model. So this shows that our model can generalize well, even though our models are trained on like general, very specific religious domain. It can actually generalize to like any open public speech. So we also developed a language identification system for 4,000 languages. For this, we use the 4,000 language MMS unlab dataset that I mentioned before. And here I compare the performance of our MMS model versus two other popular open source language identification models. So here I plot the error rate. You can see that MMS model supports about 40 times more languages. So because all the other systems have like support only 100 languages, but the MMS system supports 4,000 languages. Still the accuracy is on par with other open source systems. Similarly, we develop a speech-to-text system because we have this labeled data set of text and corresponding speech. And most importantly, like usually this is from a single speaker. So we can develop pretty good high-quality text-to-speech systems. For this, we use WITS library, which is open source library, and use that system to train models in all the 1,000 languages. Now I want to talk about the Hugging Face demo and fine-tuning that we built so that other people can use our work. So we have this Hugging Face demo that you can access in this QR code. So the way it works is you at the top you see the tab here, the speech-to-text, text-to-speech, and language identification. You select the task that you need and select the language that you want to work with and record your own voice. You can record your own voice or upload an existing audio file, and you'll see the transcriptions on the right. And similarly, you can also try this text-to-speech and language identification system. I also checked yesterday how many of the Ethiopian languages are supported here. I checked the top 4 popular Ethiopian languages, and all of them are supported by the MMS model. So we also have some scripts to like fine-tune these MMS models. So for example, if you want to fine-tune these models on a specific domain and further improve the performance, we make it possible. So we have some existing scripts that are available in the model website that I will share later. So it can be used to like add support for a new language that is not present in MMS, but you can also use it to like fine-tune an existing language and improve its performance even further. So in conclusion, I want to say that MMS increases speech technology from 100 languages to about 1,000 languages for ASR and TTS systems, and about 40x for like LID systems. But at the same time, I want to mention that we are not done yet, because there are about 4,000 written languages. Sorry. So there are about 4,000 written languages, and before MMS, we cover only like 100 languages. And with MMS, we cover like maybe 1,000 languages. But there are still like a lot of languages which needs support. And also, I also feel that even for the languages systems that we built, there's still some room for improvement. People can still fine-tune with specific data and improve its performance even further. So there's still a long road to go there. I also want to mention a collaboration that we have started recently with African Next Voices. So the main goal here is to collect high-quality speech data from different African languages and use high-quality speech models. There are some resources that you can use. Paper. Okay, that's the end of my talk. Thank you.
Thank you for the very interesting talk. So now the session is open for questions and discussions.
Hello. Thank you for the nice presentation. You mentioned that when you like collected the data, most of the data that you collected is from religious scripts. And I don't know about other languages, but what I know is in language, the language in the scripts is a bit different than what is spoken today. And I'm sure that is true with other languages as well. So how manage that gap?
Yes, so we don't want to claim that we build the best system possible for every language, but I just want to mention that previously, like before MMS, there is no system available. So this is just a start for building speech systems. But yeah, as you mentioned, like I mean, for what it's worth, we take great care, like whenever we build systems, we take care making sure that, for example, if I remember, for example, like for Azerbaijani language, there were like 2 scripts. So we made sure that we produce speech systems for like separate systems for 2 scripts. So we take great care in building the systems. But at the same time, yeah, I mean, it's hard to like deal with, I mean, one person like or one team to like know like language specific details for like all languages. So this is just a start. As I mentioned, like we provide some fine-tuning scripts as well. So there's, I mean, yeah, we can still improve, yeah, the models. Yeah.
Questions might be quite similar to what my brother has already raised. You see, the language technology researchers are highly domain dependent. So the data that you have used is rich data. How do you manage, or have you even evaluated your model for the other contexts? So have you attempted that, or how you make your model to generalized non-religious context or domain data?
Yes. So although we train the models on religious text, we don't evaluate our models on religious text. We actually evaluate our models on like open domain text. So for example, when we compare with Whisper, we compare the performance on Flow's dataset, not the religious dataset. So we want to make sure that the models, even though we train on religious text, they perform well on like open domain text. So we make some attempt there. But the problem is like there's no open domain text for like all the 1,000 languages. So we have open domain text for like about 100 languages with floors. So we made sure that the numbers on floors, like they look good, like they're not like very, very high, right? So that's something we made sure. So we also think that since we follow the same process for like all the languages, this should generalize, and the model should perform at least like decently good like on the other 900 languages where we don't have like open domain data. Yeah. Also, like as I mentioned, like we have the demo that on Hugging Face Live. You can try it and see it for yourself. Yeah. Okay. Yeah, it's possible to fine tune. Like if you have like any specific data, we can still we can fine tune.
Okay, thank you for your presentation. I would like to ask you about dialects. The way we Africans speak or Indians speak English is different from British or Americans. So how did you handle that?
Yes. So, I mean, as I mentioned, like, so yeah, there are all these challenges, like even dialects, like, so even in MMS, like, if you look at the open source page, we actually distinguish, like, for some of the languages, we distinguish, like, the dialects, but not for, like, every language. For example, like English, we have only, like, one language. We don't have, like, English, like UK English, US English, right? So yeah, we take some care, but yeah, it's not, like, not everything is taken care, yeah. But as I mentioned, like, this is a first attempt, so there is still room for improvement, yeah.
Thank you. My question is
regarding the ASR task. In reality, when people speak, they use code switching. I mean, they mix some other words of other language into another language. So what approach do you use to handle code switching when you fine-tune the wave to wake on the ASR downstream task? Thanks.
Yeah, so in this particular project, we have not focused on code switching, because I think that's a separate, so here, since we are dealing with like a large scale of languages, we first want to focus on like having like single script for each language and make it work well. For code switching, yeah, I mean, there are some approaches out there, like where you can augment the data or train models by collecting like specific code switching data. But I would say like that's an extension to what we built. But in our project, yeah, we have not taken special care for the code switching part.
Okay, thank you for your interesting presentation. I appreciate Meta's work on language. I have two questions. The first question is, does the MMS model support self-supervised learning, similar to Web2Vec? Can we pre-train the base model with unlabeled data and fine-tune it with labeled data? And the second question is, does your TTS model support speaker embedding model? When I fine-tune it, will it preserve our data voice characteristics?
Sorry, I didn't get the second question.
Your TTS model. So does your TTS model support speaker embedding model, which means it's the voice of characteristics?
Yeah, the speaker, the TTS model does not take speaker embeddings. So yeah, it produces like one speech, but although I have seen some people extend the TTS, the MMS models, and make it like produce in a different voice. I have seen some works out there, but we, at least in the paper that we present MMS, we have not worked on that. And for the first question, yeah, for the pre-training, so I mean the reason for the MMS model, right, we released the pre-training models already as open source. And we did this because like pre-training usually takes a lot of time, and doing it in a multilingual fashion with lot of data, it requires like a lot of compute resources. So that's why like we open source the pre-trained MMS models, and we hope that the research community, like if, let's say if you have small 10 hours of data in a new language, or 10 hours of data in a language you're working with specific dialect, you can use our models and fine tune it and make it pretty accurate for the task you're working with.
Any other questions?
Sorry, I am not able to hear you.
Okay, you are using common space, I mean common space for Euroman, something like that to migrate all language to English text. So, so if I speak in any language, the model will still output in that space. Then you will have some decoding to detect whether which language is it.
So the conversion for Euroman, it is done only for doing the force alignment. The reason we do force alignment is because like usually the audio files that we collect are about like 20 minutes long. So we can't use this 20-minute long audio and the transcript and train the model directly. We have to segment them into like maybe 10 or 15 seconds of speech and its corresponding transcript. So to do this, we use the Euroman conversion so that we can do the this speech segmentation into shorter audio files. But once you have the shorter audio files, we train the speech recognition systems using the language's characters. We don't use any Euroman characters for training the USR models.
Okay, thank you for your nice presentation. My question is also on the text-to-speech. I want to ask more general question, but related to your work. Do you think that the text-to-speech that you're working on can help downstream tasks on spoken language understanding, for example? And is Amharic language included in the text-to-speech work of your project?
Yes, Amharic language is included in the text-to-speech. So, but I didn't get the first part of the question.
How can it help the downstream tasks on spoken language understanding? Can we use the output of that speech to text to speech alone without adding some other natural speeches?
So are you using that using data augmentation? Is it using the data generated from TTS as a data augmentation method?
No, directly, just using it without adding some recorded speeches. Can we do some downstream tasks using only the output that you are that we are getting from your system?
Yes, I think you can do that. Also, just to mention that, so for example, when you train this speech system, right, the TTS system, for example, it may not handle the numbers properly. Like if you have like digits, like the numbers, it may not handle it properly. But if you have like characters, right, I think it should work fine. Yeah, it should work. But yeah, also the demo is in the Hugging Face demo is there, so you can actually try it on your own and see.
Thank you for the very nice presentation as well as the very interesting interactions that we had. We are really thankful also considering the availability of the data with 1,000 languages and almost more than 50,000 hours of data is very interesting, and I think a lot of researchers will use this data for their research. So please thank the keynote speaker. Okay, so